Today is the week fifth of this live tea discussion. Now, yesterday week we have studied about the eigenvalues, eigenvectors, and then we studied about the generalized eigenvectors, and then we have studied about the stability. So in this week, here we discuss about the diagonalization, the concept of diagonalization of a matrix, and then we talk about the solution of a system of an unforced system and a forced system, and then state transition matrix, etc. So, let me share my screen first. So first, I will start with a diagonalization of a matrix. So, what is basically diagonalization of a matrix? So, why we basically care about this diagonalization of a matrix? So, sometimes it is very difficult to ease the calculation. Actually, to ease the calculations of a matrix of any system, we this diagonalization is basically required, because when we diagonalize the matrix, it is now become all the elements is now become on the diagonal. There is only diagonal entries available. I mean, the matrix contain the maximum number of zero. So it is basically easier to calculate with this diagonalized matrix. So that's why for ease of calculation, this diagonalization is required. Now, the diagonalization, as we have studied previously, we have discussed in previous week that diagonalization is we have studied in previous week that eigenvalues. Studied about eigenvalues and eigenvectors. So, if a matrix have if a system have distinct eigenvalues, we have our distinct eigenvectors, right? But if system have a repeated eigenvalues, we may or may not, we may get a distinct eigenvector, but sometimes we see that we may not get a distinct eigenvector. That's why we need a generalized eigenvector things. So we will see uh, what uh, what will happen for those system who have a distinct eigenvalues, and for those system who have not a distinct eigenvalues and repeated eigenvalues, and with a not distinct eigenvectors, repeated eigenvalues, but not distinct eigenvector. I mean, we have to find out the general eigenvector case. So, basically, what we do, so we know that if A is a matrix and X, let's say X is the eigenvector of that matrix. So this is definitely square matrix, and this is eigenvector. So we have this lambda into X. This is eigenvalue, right? So what we do now, let's say we multiply A with okay. So we consider, let P be a matrix whose columns are eigenvectors of A. So if matrix A has distinct eigenvalues, that means that P matrix, so if matrix A has distinct eigenvalues, then we can say that it has distinct eigenvectors. So therefore, matrix P is invertible or okay, or non-singular, right? So if since P matrix, this P matrix has the column which is basically the eigenvectors of matrix A. So if all the eigenvectors are distinct, that means we can easily say that the matrix, that P matrix is basically invertible. We can find out the inverse of that matrix. So why it is required? Now, so P is basically x1, x2, let's say up to xn. Okay, so xn. So that means here x1, x2, xn are the eigenvectors, right? So since each eigenvector is distinct, that means we have already studied in previous week that the matrix is distinct. We have studied about the linear independency, right? So if the eigenvectors of all x1, x2, x up to xn all are the distinct eigenvector, that means all the columns are linearly independent. So that's why P we can find out the inverse of P. That means determinant of P is not equals to 0. It has some value, right? So now what we do, we multiply A with P. So what we get, A multiply with x1, x2 up to xn, right? So A multiply to x1, x2, xn. So for that case, what we get, it means ax1, which is a vector, ax2, which is a vector up to axn, right? So what we get is basically lambda1 x1, lambda2 x2 up to these all are vectors lambda n xn, right? Now how can we write this term? We can write this term as x1, x2 up to xn, and here is lambda1, lambda2 up to lambda n. Okay. So that means this lambda, so, so that means this lambda multiplied with this x1, this lambda2 multiplied with this x2, this lambda n multiplied with this lambda n, right? So which is, we will get this term, definitely. So That means what we basically started with? We started with A into P equals to this term, right? So P is this matrix. We get P into, I call this term as a big lambda. Okay. And this is basically we know P. So what we get? P into lambda. So A matrix is now, if we post multiply with P inverse in this equation, post multiply with P inverse. So what we get? A P lambda P inverse, right? So this is, so we see that here P inverse is coming into the, comes into the picture. So this P inverse always possible if the eigenvectors, that is whatever the, if whatever the columns of the matrix P, if the eigenvectors are distinct in nature, are distinct, like if the eigenvalues are distinct, then we can ensure that definitely for distinct eigenvalue we have a distinct eigenvector. For distinct eigenvalue we never get a similar eigenvector. Okay, so that's why this, because of this distinct nature of this eigenvector, P is invertible and we get the P inverse. Okay, now if P is not invertible, we have studied already how we, if system has a repeated eigenvalues. Okay, we have seen in the previous week. In previous week, we have seen that if any eigenvalue is repetitive in nature, then we may get the distinct eigenvector. So for repetitive eigenvalue, if let's say in that case, if lambda one is, let's say, repetitive in, if lambda one is repetitive twice, and for lambda one we get two different distinct eigenvector, then we can definitely construct P according this nature. Okay, because we have a repeated, we have a distinct eigenvector for same eigenvalue, same repeated eigenvalue. So definitely we can construct the matrix P. But sometimes it's possible that for repeated eigen values, we may not get the repeated eigenvectors. Like the algebraic multiplicity is not equal to the geometric multiplicity. In that case, what we do, we can we have to find out the generalized eigenvector, right? Like for lambda, let's say lambda is repetitive thrice, and it has, we are not getting the three defined eigenvector for lambda one, we are getting, let's say, one eigenvector. So that means we have to find out the two generalized eigenvector. So one eigenvector for lambda one, and by other two generalized eigenvector we have to find out using V1, using the previous eigenvector, and accordingly. I mean, for that case, you can see the previous week note, or like videos, whatever. So in that case, we get the linearly independent columns of P, and we get the P inverse. So this is basically the structure. So also what we get, we have to find out. Sorry. So from here we get this thing as well. So the diagonal matrix lambda is basically is equal to P inverse A into P. What should we do? In that case, we have to pre-multiply with P inverse, and we will get this relation. Okay. Now, okay. So this is the one thing. So why it is required? Why we are basically care about the diagonalization, right? So uh, let's say you are given a matrix A. Okay. Consider for right now, you consider that A matrix has a distinct eigenvalue. So you will have a distinct eigenvector. Okay. So let's say you are given you are given basically a matrix A, Now you are basically asked to find a, let's say a50, a to the power 50, a to the power 50. So you are basically asked to find the matrix a to the power 50. So in that case, what you should do, let's say if we do not know the concept of the diagonalization, so what we can do for this, we multiply a 50 times, and uh, we'll get the 50 a to the power 50 matrix. Okay, but this is basically a cumbersome process. This is basically a so hello, hello Arun, hello Arun, Mr. Arun
Hello.
Kumar, hello, yeah.
Yes, sir.
So yeah, so you have joined late. So I have started with a few concept. So I just repeat for you for that case. So today I am going to discuss about the diagonalization of a matrix. What is the concept of diagonalization? So since previous week you have studied the eigenvalues and eigenvector. Okay, so how this and you have already studied the generalized eigenvector wala concept, right? So here we basically talk about the diagonalization and why it is required. So it is basically diagonalization of a matrix is required to ease of computation. First of all, and we basically consider a matrix P whose columns are basically we put all the eigenvectors of a matrix into the columns. So now in previous class, as you have studied that a matrix if a matrix have distinct eigenvalue, we get a distinct eigenvector. That means, let's say if matrix have a eigenvalues, let's say a matrix is 3 cross 3 and it has eigenvalue lambda 1, lambda 2, and lambda 3. So we will get different eigenvectors for that case. And if we put the different eigenvector in the column of matrix P, we will be ensured that this P is invertible. That means it is non-singular. Okay. Now sometime it happens like in case of so sometimes it happens that a matrix may not have a different eigenvalues. It has a repeated eigenvalues, but still for repeated eigenvalues we get a different eigenvector. Sometimes we get different eigenvector. Sometimes we may not get different eigenvector. For that case, we have to compute the generalized eigenvector. So in that case, to make the matrix P invertible, if for a repeated eigenvalue we get a distinct eigenvector, we can put all the eigenvectors into the column of the matrix and we will get that this P is invertible. But if for repeated eigenvalues we do not get a distinct eigenvector, we have to find out the generalized eigenvector and put those generalized eigenvector into the matrix P, and we will see that the P is invertible as well. So this is how the diagonalization comes into the picture, the relation of diagonalization. So this big lambda is diagonal matrix. That means all the eigenvalues in a it is basically a diagonal entry, and since P is invertible, so we will definitely get a P inverse. So why it is diagonalization is required? So let's say you are given a matrix A and you are asked to find out a matrix A to the power 50. So if you do not have the concept of diagonalization, what you do that you multiply A 50 times. But this is basically a cumbersome process. It is basically a complex computation. Computation, it is basically very complex. Let's say you have to ask, you are asked to find out A to the power 500. So you have to multiply 500 times, which is very difficult. But in case of diagonalization, what you can do, let's say we know that A is equal to P lambda P inverse, right? So what is A square? A square should be A big lambda P inverse into P big lambda P inverse into P big lambda P inverse, right? We multiply this twice. So we know that P big lambda P inverse P big lambda P inverse. If inverse, we know that P inverse exists. So this is means basically identity matrix. So what we get? P lambda square P inverse. That means A square equals to this term, right? Similarly, A cube equals to P lambda cube P inverse. And similarly, if we do A to the power 50, we get P lambda to the power 50 P inverse. So in case of lambda to the power 50, since lambda is a diagonal element, that means P and lambda contains, let's say, all the diagonal element lambda 1 to lambda n to the power 50 P inverse. So in that case, what you have to do is basically this. This is basically lambda 1 to the power 50, lambda 2 to the power 50 up to lambda n to the power 50 into P inverse. So you do not need to multiply A 50 times. You just have to find out this matrix and pre-multiply and post-multiply with P and P inverse, you will get A to the power 50. So this is basically you ease your calculation. So let's start with a small example. Okay. So you have a matrix. You are given basically a matrix A is equal to 0.8, 0.2, 0.3, 0.7. So this matrix has a special features. This matrix is called a Markov matrix, first of all. So which type of matrix we call a Markov matrix? You have to see that if the columns, the elements of column, if we add the elements of a column and it's added, I mean, if you get a 1, 0.8 plus 0.2, we'll get 1, 0.3 plus 0.7, we'll get 1. So if this happens, so this matrix is basically called a Markov matrix. So this is basically a small information. There's nothing about this diagonalization. So now you have to find out the A minus lambda I equals to 0. So you have to find out the eigenvalues, which is 0.8 minus lambda 0, sorry, 0.3, 0.2, and 0.7 minus lambda equals to 0. So what are the values of lambda you will get? You will get lambda 1 equals to 1 and lambda 2 equals to 0.5. Yeah. So we know that A equals to P lambda P inverse, right? So now you are first, I'm just okay. So now you are asked to find out the value of A square. So what you should do, P, oh, first of all, you have to find out the eigenvectors. Okay. So what are the eigenvectors? For eigenvectors, what should you do? A minus lambda 1 I into V1 equals to 0. Okay. So what is A minus lambda 1 I? I put the lambda 1 over here. It is minus 0.2, 0.3, 0.2, and minus 0.3. So this is V11 and V12. This is 0, 0. So what is this? It's basically minus 0.2 V11 plus 0.3 V12 equals to 0. Okay. So what eigenvalue we get? So if eigenvector, the first eigenvector is basically, yeah. So V1 is equals to 0.6 and this is equals to 0.4. Okay, so V11 is basically 0.6 and V12 is 0.4. Okay, and what for eigenvector A minus V2I, sorry, A minus lambda 2 I into V2 equals to 0. So what you should do is what lambda, sorry, this is lambda 1, let's say. Okay. So what you will get, it's basically 0.3, and this is 0.2, and this is V21, V22. This is equals to 0, 0. So what you will get? You will get the matrix V2 is basically 1 minus 1. So this is basically your two eigenvectors. Okay. Now we can construct P matrix. We can construct P matrix using this. We put the column into the put the eigenvectors into the column of matrix P. So what we get? It's 0.6, 0.4. This is 1. This is minus 1. Okay. So now you are asked to find out A square. So A square is basically, as we have seen, P into lambda square P inverse. And what we get? This is 0.6, 0.41 minus 1. Here lambda square. So lambda square is basically 1 square, 0.5 square, 0, 0. And here is basically P inverse. So what is P inverse? Okay, we have to find out the P inverse over here. Let's say we put this aside and we'll find out the P inverse first. So P inverse is equals to adjoint P by determinant of P, right? So what is adjoint? So what is basically determinant of P? Determinant of P is 1 by minus 0.2 over here. Sorry, 1 by minus 1. 1 by minus 1. Sorry. 1 by minus 1. And the adjoint is basically, what is adjoint? This is minus 1. This is 0.6. This is minus 1. This is 0.4. Right. This is the adjoint. And what we will get? The P inverse is basically 1, 1.4 minus 0.6. Right. This is the P inverse we get. And now we find out this. What we'll get? 1, 1.4 minus 0.6. Okay. So, what did we get? 0.4. This term is 100.25. 1.41 minus 0.6. Okay. Now 0.6, 0.4, 1 minus 1. So 1, this is 1. This is 0.4 into 0.25. 0.4 into 0.25, what we get is 0.1. And this is 0.6 into 0.25, what we get? Minus 0.15. And we will get 0.7, 0.45, 0.3, 0.55. So this is the value of A square we get, right? That means from here we can see that A to the power k is basically P into lambda to the power k into P inverse. Now, if k is tends to infinity, what we get? We get A to the power, let's say, limit k tends to infinity A to the power k. What value we get? we get limit p lambda to the power k, this is k tends to infinity, p inverse, right? So that means what happened? It is 0.6, p is 0.6, this is 0.4, this is 1, this is -1, and now k is tends to infinity. So k is tends to, if k is tends to infinity, 1 to the power infinity is always 1. This is 0, this is 0, and now k is tends to infinity. So definitely this is a decimal term. 0.5 is a decimal term. If we square it, cube to the power 4 to the power 5, the value is definitely decreasing. And k tends to infinity, that means we get this value is 0, and this is become 1.4 minus 0.6. Right? So ultimately what we get this is 0.6, this is 0.4, 1 minus 1, and here we get 0.4, sorry, here we get 1, 1, 0, 0. So what we get 0.6, 0.6, 0.4, 0.4. So limit k tends to infinity, a to the power k, we get this value. Okay. So basically, it is very easy to calculate the, matrix power, you can say. So the next example that I'm going to talk about. So next example I'm going to talk about is basically Fibonacci series. So we know that Fibonacci series, the Fibonacci series we know about, because it's basically, let's say, if what this series. So Fibonacci series basically, let's say we have to we are basically given 2.0 and 1. Let's say we are given a 2.0 and 1. Now we can find out the Fibonacci series. So the next term would be 0, 1 plus 0, that is 1. The next term would be 1 plus 1, that is 3. Sorry, that is 2. Then 1 plus 2, that is 3. Then 2 plus 3, that is 5. Then 5 plus 3, 8. Then 13. And this is continuous. So this series is basically called, Fibonacci series. Now I'm going to make a question out of this Fibonacci series. So what is the question? So question is, the initial number of numbers of Fibonacci series are, let's say, if f1 equals to 0, sorry, f not equals to 0, and f1 equals to 1. Okay. Then find f100. Okay, this is the question is given to you. So you are given basically, you are basically told that, okay, you are given a Fibonacci series. The first two term you are told, first two term is basically 0 and 1, that is given in the question. And now the question asked is, you have to find out the f100, like the 100th element. You have to find out the 100th element. Okay. So not 100, it's, you have to find out the 101th element, because Zeroth element is basically 1. First element we termed as a 0. So you have to find out the 100th element. Okay. So how we find out this element? So, what we have seen in here over here is basically we know that f k, I mean, let's say f2, we need to find, to find out the f2 we need f1 and we add it to f0, right? So to find f3 we need f2 plus f1. f4 we need f3 plus f2. Similarly, for f100 we need f99 plus f98, right? Yeah. So this is the thing. So how we can put this as a systematic structure? Let's say I have considered that x is f k plus 1 and f k. So I call it as a xk. Okay. So what we see that fk plus 2 is basically fk plus 1 plus fk, right? This is the picture from here we get fk plus 2. If k equals to 0, f2 is equal to f1 plus f0. Then if k equals to 1, f3 is equal to f2 plus f1, k is equal to 98. Then what we get? f100 is equals to f99 plus f98. Okay. And the next term is fk plus 1 is equal to, we know that fk plus 1. So what we get? Fk plus 2, fk plus 1 is equals to 1, 1, 1, 0. And here fk plus 1, fk, right? So what is this? This is nothing but a xk plus 1. If we consider k is equal to k plus 1, then here fk plus 2 and fk plus 1. So this is basically k plus 1. This is basically a and this is basically xk, right? So how we can find out the value of f100? So as you see, let's say here f101, f100 is equals to 1110. So let k equals to 99. Okay. So if k equals to 99, so f101 or f100, this is equals to what we get, f100 and f99, right? Now if f100 and f99, what we get? We get 1110, and here is basically f99, f98. Now if we put this term, if we put this term over here instead of f100, f99, if we put this whole term, so what we get? So we get f101, f100 is equals to 1110 whole square, f99, f98, right? This is we get. So now, since we are basically given only two numbers, that is f0 and f1, right? So what we have to do? We should do f101, f, because we do not know f99, f98. We only know f1 and f0. So from here, what we do, 1110, this whole to the power 100 multiply with f1 and f0, right? Now you have to find out this term. So once you find out this term, you multiply with f1 and f0 because you know the value of f1 and f0, and you will get f101 and f100, right? But the problem is you have to multiply this a term with 100 times, which is very difficult work. So now using diagonalization, we can do it easily. So first, what should we do? We have to find out the eigenvalues. So for eigenvalues, what should we do? A minus lambda I equals to 0, right? So I'm not going into the detail of how to find eigenvalues because you all know how to find eigenvalues. So I'm just writing the answer. So what are the eigenvalues? So lambda 1 is basically 1 plus root 5 by 2, and lambda 2 is 1 minus root 5 by 2. These are the two eigenvalues that we get by solving this equation. Right? So now we have to find out the eigenvectors. So how to find the eigenvectors? The first is a minus lambda 1 I v1 equals to 0, right? So what should we do? We do a minus lambda 1. So 1 minus lambda 1. So basically 1 minus lambda 1, 1, 1 minus, sorry, this is 1 and this is minus lambda 1 into v11, v12 equals to 0, 0. Okay, so what now I have to do is put the value of lambda 1. What I get 1 minus 1 minus 1 plus root 5 by 2. This is 1, this is 1, and this is minus 1 plus root 5 whole divided by 2. Here v11, v12, this is 0, 0. Okay. So what we get? We get here we get 1 minus root 5 divided by 2, 1, 1, minus of 1 plus root 5 whole divided by 2. So what can value of v1 we take? So if we consider this is v11, if we consider v11 as 1 plus root 5 whole divided by 2 and v12 1, we will get this option, we will get this thing, right? How? So v11, so what is basically, okay, first of all, let me write down the equation. It's 1 minus root 5 whole divided by 2 into v11 plus v12 equals to 0. I'm just writing down the first equation. Okay. What we get, or let's say if I write down the second equation, it will be better. So v11 minus 1 plus v12 equals to 0. Okay. So if we put v11 equals to 1 plus root 5 by 2 and v12 equals to 1, definitely we can satisfy this equation. And also 1 minus root 5 by 2 into 1 plus root 5 by 2, you will get minus 1. So definitely you satisfy the first equation as well. Okay. Right, on the first equation as well. Okay. So my first eigenvector is, this is basically 1 plus root 5 by 2. This is 1. And what is the second eigenvector? Similar way. So if you do the similar structure, you will definitely get this thing. 1 minus root 5 whole divided by 2. Here, 1. So this V1 and V2, since we get a distinct eigenvalue, so these V1 and V2 definitely linearly independent. They are definitely uh, uh, if we put a matrix, if we put all these eigenvector into a matrix column, the matrix is definitely a non-singular matrix. Okay, so this is P. So P inverse, for P inverse, what should we do? This is adjoint of P divided by determinant of P. So what is determinant of P? This is 1. So determinant of P is basically half plus root 5 by 2 minus half plus root 5 by 2. So this is basically nothing but a root 5. So 1 by root 5 is over here. And what is adjoint? Adjoint is nothing but 1. This is minus 1 minus root 5 by 2. This is minus 1 and this is 1 plus root 5 by 2. So this is P inverse. Okay. So now what I have to do, I have to find out a to the power 100, right? A to the power 100, which is basically P lambda to the power 100 into P inverse. Okay. So this is basically what is P? 1 plus root 5 by 2, 1, 1 minus root 5 by 2, 1. Okay. And here lambda 1 plus root 5 by 2 whole to the power 100, 0, 0, 1 minus root 5 by 2 whole to the power 100, and then multiply with P inverse. So P inverse is basically 1 by root 5. Here 1 minus 1 minus 1 minus root 5 by 2 and 1 plus root 5 by 2. So if we multiplication, if we do the multiplication, ultimately what do we get? We get a very big matrix. So we get 1 by root 5. This is a scalar term. We can put it in a put it outside, and what we get 1 plus root 5 by 2 whole to the power 100, 1 minus 1 minus root 5 by 2 whole to the power 101. Here 1 plus root 5 by 2 whole to the power 100 minus 1 minus root 5 by 2 whole to the power 100. Okay, and what do we get over here? So we'll get minus 1 minus root 5 by 2 into 1 plus root 5 by 2 whole to the power 101 plus 1 plus root 5 by 2 into 1 minus root 5 by 2 whole to the power 101. Similarly here, same thing, just to the power 100. So this is the matrix that we get, right? This is basically a to the power 100. And now what? This is not our target. Our target is to find out the F100. So F101, F100 is basically a to the power 100 into F1, F0. So this is basically a to the power 100 into 1 and 0. So if we do these things, if we multiply a to the power 100 with 1, 0, what we get? We get 1 by root 5, only first column we get, right? 1 plus root 5 by 2 whole to the power 100 minus, sorry, 101. 1 minus root 5 by 2 whole to the power 101. And here 1 plus root 5 by 2 whole to the power 100 minus 1 minus root 5 by 2 whole to the power 100. So my F100 is basically this term, the last term. So this is my F100. So this is how we basically use the diagonalization to ease our calculations. Okay. So now next, I'm going to the next thing is the solutions of a matrix, solution of a system. Sorry. So forced and unforced system, solution of a system. Talking about forced and unforced. So what is unforced system? So if we say the system is x dot equals to ax, so there is no u. So this is basically unforced system. That means system is driven by its initial condition. Okay, system is not there is no external input to the system which by which the system is basically driven. Okay, so the system is driven by only its initial condition, and x dot equals to ax plus bu. So this is forced system. The forced system means you have to apply some u to the system so that system move. Okay, like you see that in previous class, previous TA discussion, live discussion, we have seen, you have seen basically that no yeah in sorry, I just forget in a pendulum scenario, in pendulum case. So if you see in lecture 4, sorry, week 4 discussion, you see there is a pendulum. Okay, so this is basically this system, this pendulum system. You see, there is a no u over here. So this is basically, though this is a non-linear system, I'm just talking, I'm just giving you an example, the unforced system example. So it's basically driven by its initial condition. Whatever the initial condition you are given, that is by which this system is basically move. There is no input, external input in this system. So this kind of system is unforced system. So here I'm going to talk about the linear system. So first, sorry, for this unforced system, so this is basically, what is this? This is basically dx by dt. So dx by dt equals to ax, we all know. So if we integrate it, what we get, let's say from if we consider, so consider t0 equals to 0. So from 0 to t, dx by x equals to from 0 to t at, sorry, a dt. So what, simple calculus, this is basically uh, sorry, I have a very big mistake over here. Okay. Here is from, and if there is some x0, initial condition is over here, because I am here, this side is basically from x0 to x, dx by x, and here is basically from 0 to t, a dt. So this is basically ln x by this is basically ln x by x naught to the initial condition is equals to a into t, because 0 is not over here. So now x by x0 equals to e to the power at. So what we get, x equals to e to the power at into x0, right? If t0 is not 0, in that case, let's say this is xt, x of t, x of t, this is x of t, this is x of t. So what we get, x of t equals to e to the power a t minus t0 x0. Okay, so uh, this is for unforced system state space. And for forced system case, if we talk about the forced system, what we get, and this term is called state transition matrix. This is also called state transition matrix. Okay. Now for forced system, if the system is forced one, that means for this case x dot equals to ax plus bu. Okay. So in that case, dx by dt same ax plus bu. Okay. Let's not do this. It's not required. So x dot minus ax less is equals to bu. Now we have studied in integration in plus 2, in 11 12 in plus 2, we have studied about the integrating factor and how to integrate. So definitely this is basically, if we differentiate e to the power minus at x of t, what we get, this is basically the d dt of e to the power minus at into x. I'm just skipping the x of t term, just of t term I'm just skipping. And here e to the power minus at, this e to the power at basically in integrating factor. We have all studied about this into x, right? So what we get, this is minus a e to the power at into x, and this is e to the power minus at into x. So if we take a common, take common, what we get? We get e to the power this is x dot. Okay, and this should be yeah, this is x dot, and this should be, if we take common e to the power minus at, so now we can write this term in this format as well, e to the power minus at into a. We will see in next that how this a, because this two a and a is also a matrix, and e to the power at, a is also a matrix and e to the power at is also a matrix, but these two matrices basically commute. Okay, we will see how these two matrices commute, because in general AB is not equals to BA. If A and B are both are the matrix, then AB is not equals to BA. We know that. But here we will see that these two sometime matrices are commute. Basically, AB equals to BA. It happens. So here A and e to the power minus 80. These two are basically uh, uh, these two matrices basically commute. This is what I am trying to say. X plus, do it in that format, e to the power minus 80 x dot minus e to the power minus 80 a x. So e to the power minus 80, it's x dot minus ax. Okay. So multiply here, pre-multiply with both e to the power minus 80 x dot minus ax equals to e to the power minus 80 bu. So this term we can write it as a d dt of e to the power minus 80 x equals to e to the power minus 80 into bu. Right. Now we integrate both sides. What we get? This is basically x0 to x of t e to the power minus 80 x, and here this is t0 to t e to the power minus a tau b u d term, right? So this e to the power 80, this term, so this e to the power 80, this term is basically not relevant over here, because here I am going to integrate with respect to dx. So we can put it over here, x of t x dx. Sorry. So this is the thing. So this is the thing. So what we get, e to the power minus 80 into x of t minus e to the power minus 80 into x0. This is equals to e0 to e to the power minus a tau bu d tau. Okay. So if I take a common of e to the power minus 80, what we get, xt minus x of 0, which I cross multiply this over here. So what we get, t0 to t e to the power 80 is a t minus tau b u into d tau. Just a minute. I think I've made some mistake. Just a minute. I have to check. I think I made a mistake over here. I'm just not able to find out the mistake. So So yeah, the mistake is, yeah. So this should be AT0. Okay. And this should be AT x of t equals to e to the power minus AT0 x0 plus integration t0 to t e to the power minus a tau bu d tau, and then I have to take common xt equals to e to the power a t minus t0 x0 plus t0 t e to the power a t minus tau bu d tau. So this is basically for force system case. Okay. Now we will see a few examples, and then if you do not have, okay, so then we will wrap it up. Okay. Now if t not equals to 0, then it will become simply 8 e to the power 8. So the examples, okay, first I'm going to see force system, a unforced system example. So the system is x dot equals to ax, where let's say x dot equals to 0 1 minus 2 0 into x, given x at t equals to 0, that is x0 equals to 1 1, and y equals to, this is the matrix. So what's the question? Obtain the time response of the system. So obtain the time response of the system. Okay. So here we know that time response of this is xt. This is unforced system x dot equals to ax. So definitely this is xt equals to e to the power 80 into x of 0. Okay. Now in if you take in Laplacian form, this e to the power this is basically e to the power 80 is basically Laplace inverse of Si minus A inverse. Okay. So just after this few example, I will discuss about the state transition matrix and all that. What are there are the few properties of state transition matrix, and then we will wrap it up. So first, we see that how this will happen. So Si minus A. So first you have to find out the Si minus A, right? So Si minus A is basically A is 0 1 minus 2 0. So S minus 1 to S, right? This is Si minus A, and I have to take a inverse. So Si minus A inverse is basically adjoint of Si minus A divided by determinant of Si minus A. So first we have to find out the determinant of Si minus A. So determinant of Si minus A is basically what is A square plus 2, right? So this is basically determinant of Si minus A. Now adjoint of Si minus A is basically cofactors and then transpose. The cofactor of S is S, cofactor of minus 1 is cofactor with sign, cofactor of minus 1 is minus 2, right? And then cofactor of 2 is minus of minus 1, and cofactor of S is A. S is S. And then it's transpose. So what we get is S1 minus 2 and S. Okay, so this is the adjoint. So Si minus A inverse sorry is S divided by S square plus 2, 1 divided by S square plus 2, minus 2 divided by S square plus 2, and S divided by S square plus 2. Okay, now you have to find out the Laplace inverse of this Si minus A inverse. The Laplace inverse of Si minus A inverse is so Laplace inverse of Si minus A inverse is this is basically what is this? This is basically cos of root 2t. This is yeah, this is basically 1 by root 2 sine of root 2t. This is basically minus 2 by root 2 sine of root 2 into t, and this is basically cos of root 2 into t. Right. So this is your system. Hey, sorry, this is your state transition matrix. Sometimes this state transition matrix is also written as a phi t. Okay. So phi t is basically cos root 2 into t minus root 2 into sine root 2 t 1 by root 2 sine root 2t and cos root 2t. Okay. So x1 t x2 t is basically this term into x0. That x0, what x0 we are given? 1 1. Okay. So 1 1. Okay. So what we get? We get cos root 2t plus 1 by root 2 sine root 2t and then minus root 2 sine root 2t plus cos root 2t. This is what we get. So now you have to find out the output response. So y is given 1 minus 1 x1 x2, right? So this is basically x1 minus x2. So what is yt? So output response is basically cos root 2t plus 1 by root 2 sine root 2t minus plus root 2 sine root 2t minus cos root 2t. So this to eliminate, and it would be 3 by root 2 sine root 2t. So this is basically your output response, right? This is basically your output response. Now, the next example is I'm going to talk about. It is on forced system. The system is given to you, and you have to find out the value. Let's start do this example. So you are given a system. The system is x1 dot equals to minus x1 plus x2 and x2 dot equals to minus 2x2 plus ut. Okay. So given initial condition is given to you, that is x1 0 is -1 and x2 0 is 0. And what else is given to you? And ut is, it says 1 for t greater than 0 and it is 0 for t less than or equals to 0. Okay. So it is verified. Uh, from here, so what type of input signal is this? So this is basically, what type of input signal is this? This is basically a step input, right? Because we know that step input so this is basically step input, right? It says that at t less than 0, it is always 0. And when t greater than or equals to 0, you will get a response. So this is basically t and this is ut, right? So this kind of signal is it is. So now we will find out the system. Put it in a state space, find out the A matrix. Is nothing difficult to find out the A matrix. 1 1 -2 0 x1 x2 plus 0 1 u. Okay. So for fourth system case, just here I'm just put a note box over here. Let's say do it in a different color. So put a note box over here. So we know that x dot equals to ax plus bu. Okay. So take a Laplace transformation. So when first of all, take a Laplace transformation. So it is s of xs equals to a into xs plus b into us. So here xs, sorry, si minus a xs equals to b us, right? Oh, sorry, here one mistake that I have already that I did is consider the system has initial condition minus x0 or rather I can do it over here. This is x0 plus b us. So this is si minus a inverse x0 plus si minus a inverse b u of x. Okay. So from here, xt is basically the Laplace inverse of si minus a inverse x0 plus this Laplace inverse of si minus a inverse into b into us. Okay. So this is the actual thing. So what we have to do, we know the system matrix, that is A is given to you. So what is A? A is -1 1 -2 0. So you have to find out the si minus A. which is nothing but s plus 1 minus 1 to s, right? And then si minus a inverse is basically determinant, which is s square plus s plus 2, and adjoint of si minus a, which is s 1 minus 2 and s plus 1. So what we get s by s square plus s plus 2 minus 2 by s square plus s plus 2. This is 1 by s square plus s plus 2, and this is s plus 1 by s square plus s plus 2. Right, okay. Oh, I'm extremely sorry. Sorry, this is x2 over here. This is not x1. So this should be 0. This should be minus 2. You just need to check this is not x2 over here. This should be, yeah, this should be 0. This should be minus 2. So this should be 0 and this should be s plus 2. So this is, sorry, this is my fault. This is s plus 1, s plus 2, and here it would be s plus 2, 1. This should be 0. So here this should be s plus 2 by s plus 1, s plus 2. So this should be s plus 1. This is 1 by s plus 1, s plus 2. This is 0. And this is s plus 2. 1 by s plus 2. Okay. So we can do one thing. We can do, so what we can do? We can do 1 by s plus 1 minus 1 by s plus 2. This is one term. This is 1 by s plus 2. If we take a Laplace inverse of si minus a inverse, what we get? This is the Laplace inverse. If we take the Laplace inverse of here, it is e to the power minus t. This is e to the power minus t minus e to the power minus 2t. This is 0, and this is e to the power minus 2t, right? Okay. So this is one term you get. So next thing that you get, you have to find out the Laplace inverse of si minus a inverse b into us, right? So this is step input. So sorry. So this is step input. So for step input, what we do? So ut, this is we have to find out. Okay. So we know ut equals to 1 for t greater than or equals to 0. So what would be the us? This should be 1 by s, right? That we know. So what is the thing that Laplace inverse of si minus a inverse into b into us, right? So the Laplace inverse of si minus a inverse, what is si minus a inverse? It it is 1 by s plus 1, s plus 1, 0, 1 by s plus 1 minus 1 by s plus 2, and 1 by s plus 2. Into b, it is 0, 1 into 1 by s. So what we get 1 by s plus 1 by s plus 1 minus 1 by s plus 2 and 1 by s plus 2. This term into 1 by s into 1 by s, right? So what we get, 1 by s into s plus 1 minus 1 by s into s plus 2 and 1 by s into s plus 2. We can do this. This is Laplace inverse 1 by s minus 1 by s plus 1. Okay, minus, I have to find out half into 1 by s. It's better I write it down over here. 1 by s minus 1 by s plus 1 minus half into 1 by s and this is minus minus plus half into 1 by s plus 2, right? Yeah. So I just basically over here what I did, I just split it. This two term, I just split this term into here and this term into this term. Okay, nothing exceptional. And this is basically half into 1 by s minus 1 by s plus 2. Yeah. So what is the so then what I get is basically half into 1 by s minus 1 by s plus 2 minus 1 by s plus 1 and here half into 1 by s minus 1 by s plus 2. What is the Laplace inverse then? So Laplace inverse is then half 1 minus e to the power minus 2t minus e to the power minus t. Sorry, this is plus. I made a mistake again. And here half into 1 minus e to the power minus 2t. Okay. So the complete response xt is, we know that Laplace inverse of si minus a inverse into x naught plus Laplace inverse of si minus a inverse into b into us, right? So what is si minus a inverse? Si minus a inverse is basically this term, e to the power minus t, e to the power minus t minus e to the power 2t. So this term, okay. So e to the power minus t, e to the power minus t minus e to the power minus 2t, 0, e to the power minus 2t into x0. What is x0? What x0 we get? We were given minus 1 and 0. Okay. So this is minus 1 and 0. And what value over here? This term is half 1 plus e to the power minus 2t minus e to the power minus t and half 1 minus e to the power minus 2t. So first term is minus e to the power minus t and this is 0. This is 0 plus half 1 plus e to the power minus 2t minus e to the power minus t and half 1 minus e to the power minus 2t. So what is xt? Xt is basically half plus half e to the power minus 2t minus 2 e to the power minus t, and here half minus half e to the power minus 2t. So this is basically your answer for force system case. So here we have seen two example, one from the force system, one from the unforced system, and this is how you find out the system's response. So now so here basically when we find out the system's response, here we see the lots of what we get involvement of state transition matrix, right? We see lots of involvement of state transition matrix. Now this state transition matrix have some property. So this state transition matrix, sometimes it is called phi t. This is called e to the power at. This everything. This is also a state transition matrix. So the first thing is this is basically a fundamental matrix. I'm not going to write down the all of things. I'm just going to I will say and few things I will write down. This is basically fundamental matrix. Okay. So and also phi t comma t is also denoted as phi t minus t, that is phi 0 is basically identity, right? Next, phi t minus t1, phi t1 minus t naught, and phi t2 minus t1 is basically phi t2 minus t naught. So here, this is nothing to worry about. I mean, nothing to discuss about, because we know that phi t minus t1 minus t naught is a to the power t1 minus t naught into a to the power t2 minus t naught. So what we get, e to the power 8t1 into e to the power minus 8t naught into e to the power 8t2 into e to the power minus, sorry, this should be t1, 8t1. So this two term is basically identity, and what we get e to the power 8t2 minus t naught, so which is basically phi t2 minus t naught, right? So now next thing we have talked about, we know we have studied in +2 level that E series. We have studied in +2 level about E series. It is basically 1 plus x plus factorial 2x square plus 1 by factorial 3x cube plus in that way, right? This is the infinite series, X series we have studied. Now here we will study about the matrix exponential, that is e to the power at. So the A is the matrix and T is the scalar term. So what is this? So instead of 1, it would be I plus AT. Okay, this is the matrix, because multiply a matrix with a scalar is always the matrix, plus factorial 2 AT square plus factorial 3 AT cube, and it will continue in that way. So in previously I have said that d dt of e to the power at, which is basically a e to the power at. This is also equals to e to the power at into a. Okay. So that means these two matrices a and e to the power at, these two matrices basically commute. Otherwise, this won't be happen. Okay. So how it will commute, we will see that. So from here, if we derivative this term, if we differentiate this term, so d dt of e to the power 80. So the differentiation of I is basically 0 because I is the constant term. 0 plus a, because a is a constant matrix and multiply with t. So t, only t will be there. There is a only there is a derivative of t plus 1 by 2 into 2 a square t. So this plus 1 by 6 into 3 a cube t square plus 1 by 24 into 4 a to the power 4 t cube. It will continue in that way, right? So we can write this in that format: 0, no need to write the 0. So a plus a square into t plus half, which is factorial 2 into a cube into t square plus 1 6, which is factorial 3 into a to the power 4 into t cube, plus in that way. Now take a common a. So what we get, take common a, what we get is at plus half a square t square plus factorial 3 a cube t cube plus. So what is this term? This is basically nothing but a e to the power 80, right? So this is a into e to the power 80. Now I take common a from I take common a previously, right? Now if I take common from here, uh, if I do this kind of thing, let's say I plus at plus a square t square plus a cube t cube plus dot 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 to a. We can also do this thing because t is always a scalar term. So we basically multiply a with a square with a cube with a. So this is basically e to the power at into a. So for state transition matrix, e to the power 80 into a is equals to a into e to the power 80. Okay, this is the thing. Now we will see a few examples on state transition matrix. Okay. Okay. So the example is a equals to, you are given 0, 1, minus 2, 0. Find the now here we will do the state transition matrix. We previously see in previous example we have seen that you have to just find out the SI minus A inverse and take the Laplace inverse of that SI minus A inverse. You will get the e to the power 80. Now here we will try this, try to find out this state transition matrix using this series. Using this series, we are basically trying to find out this state transition matrix. Okay. So phi t or e to the power 80 is basically, we know, a 80 plus factorial 2 a square t square plus 1 by factorial 3 a cube t cube plus this. So now here a is equal to 0, 1, minus 2, 0. Now a square equals to 0, 1, minus 2, 0, multiply twice. It's minus 2, 0, 0, minus 2. A cube is basically a square into a, which is minus 2, 0, 0, minus 2, 0, 1, minus 2, 0. What we'll get? We get 0, 2, minus 4, 0. Sorry, minus 2 is multiplied with 0, minus 2, 4, 0. Okay. So what is e to the power 80? E to the power 80 is basically, first is I, 1001, then is 80, 0, t, minus 2t, 0. T is multiplied with that. Next is half or factorial 2 into a squared t. What is minus 2t square, a square t square, minus 2t square, 0, 0, minus 2t square. And then factorial 3, it's 0, minus 2t cube, 4t cube, and 0. Right? So what we get? We get 1 plus 1 by factorial 2, and factorial, this is t square, 1 plus t square, yeah, sorry, 1 minus t square, and it is continuing that way. Here what we get is t added with 2 by 6 minus 1/3 t cube, and it is continue that way. Here minus 2t, 4 by 3, minus 2t plus 4 by 3, 4 by 6, 4 by 6 means 2 by 3 t cube. Continue this way. And what is this term? It's 1 minus t square, and it's continue this way, right? So this is the thing that we get. So now what we can do? We can do, this is basically, you can see that this is basically a series of cosine series. This is basically. So how we'll see that this is t square. So what you can do is basically, okay, let's, instead of writing it as a t square, I'm just writing it as a 2t square by 2, and then it is continue. This is also 2t square by 2, and this is t minus 1/3. Okay, 2 by factorial 3, and it is 4 by factorial 3. So we can write it in that format, t square by 2, and then it will be a cube t square by factorial 3. So here it would be root 2 by root 2 into t minus root 2 2 cube, or it's 2 root 2 by root 2 into t cube by factorial 3, plus in that way this is similarly root 2 into root 2t minus root 2 into 2 root 2 t cube by factorial 3, plus this way, and this is 1 minus root 2 square t square by 2 plus this way. So what we get, so this is basically a cos root 2t. This is basically minus root 2 sine root 2t. This is basically 1 by root 2 sine root 2t. And this is basically cos root 2t. So definitely the finding out the state transition matrix using Si minus A inverse is very much easier, and taking the Laplace transform, it is very easier to find out the state transition matrix rather using this term. I mean, rather using this infinite series term. It is quite difficult, but still you can find using infinite series as well. That is the basic purpose of showing this. You always no need to find out the Laplace transform. You no need to find out the Si minus A inverse, and then you find out the Laplace transformation, inverse Laplace transformation of Si minus inverse, and then you do this kind of thing. Because sometimes here is basically the matrix is 2 cross 2 matrix, but if the matrix is 4 cross 4 or 5 cross 5, in that sorry, in that case it is quite difficult to find out the Si minus A inverse, right? So for that case, you can easily, I mean, this method is basically easily, it is not, I would not say it is easy, because here you also find out the A square, AQ and all that, but still, sorry, but still somehow this is quite easier to find the value of Si minus, find the value of state transition matrix. Okay, I'll just discuss one thing, and then I'll wrap this whole thing. So one short thing that I forget to discuss. So if your system, if system matrix, which sometimes called A matrix, is in controllable canonical form, then its eigenvector, let's say the controllable canonical form means, let's say A is equals to 0, 1, 0. I'm taking only 3 cross 3, 0, 0, 1, and minus, what is controllable canonical form? It's minus A1. Let me check. Yes, it's minus A0 minus A1 minus A2. If it is in this format, it is easier to find out the modal matrix. What is modal matrix? That P matrix that I have said previously, the P matrix that I have said previously, which columns contain only the eigenvectors, is basically a modal matrix. So it is basically easier to find out the modal matrix for this kind of scenario, for this kind of case. So what is the modal matrix? So it has eigenvalues. Let's say lambda 1, lambda 2, and lambda 3. So it is very much easier. 1 by lambda 1, lambda 1 square, 1 by lambda 2, lambda 2 square, 1 by lambda 3, lambda 3 square. So in that way, you can, so this is one eigenvector. So this is one eigenvector. this is another eigenvector, and this is third one eigenvector, and you put it in a column of this vector. So it is easier to find out. The next thing is okay. Okay. So the next thing is you can always, let's say you we know that diagonalization is I mean basically it makes easier to find the values, easier to find the easy for the computation purpose, right? We know that this is basically very easy. So what diagonalization that we have seen, A is equal to P lambda P inverse, right? So, and we know that this lambda, I'm just here writing down in a 2 cross 2 format. You can convert it into 3 cross 3, 4 cross 2, or n cross n format. Okay. So we know that this is always happen, right? This lambda is in this format. So if it is in this format, it is very easy to find out e to the power lambda t, right? It is nothing to worry about, because this is e to the power lambda 1 t, 0, 0, e to the power lambda 2 t. So basically, it is very easier to make any calculation using this diagonal matrix, right? So this is not A, this is lambda. Okay. Now, if you are asked to find out e to the power at, okay, another thing you can do, you first find out this e to the power lambda t, and then you can do these things. So from here, uh, I just show you this. So now A is multiplied with, let's say, scalar t. This t is scalar. So what we get, P lambda P inverse multiplied with scalar t. So since t is a scalar, we can put it anywhere. It doesn't create any problem. We put it over here, lambda t. Now take an exponential both side. E to the power at is equals to e to the power p lambda t p inverse. Okay. Now you just split it in a series format. What is this? E to the power. So this is I plus p lambda t p inverse plus factorial 2 square p inverse into p lambda t p inverse plus factorial 3 cube p lambda t p inverse p lambda t p inverse and p lambda t p inverse, and you can continue this process. Okay. So what you will get is e to the power at, this is I plus p lambda t p inverse. First term. Second term is this p and p inverse create a I. So it is p lambda t square p inverse. And then this p create a I, p inverse p, and this p inverse p create a I. So we'll get factorial 3 p lambda t whole cube p inverse, and continue this way. Okay. Now we can write I in terms of p P inverse plus P lambda T P inverse plus factorial 2 P lambda T square P inverse plus 1 by factorial 3 P lambda T cube P inverse plus it is continuing that way. So e to the power at equals to take P common from left side I and take P inverse common from right side. So we get I plus lambda T whole square by factorial 2 plus lambda T whole cube by factorial 3. So this term is basically e to the power at equals to P e to the power lambda T P inverse. Right. So you can find out e to the power at using this diagonalization process e to the power lambda T. Using this term, you can find out the e to the power at. So, so in that way, you can easily find out the state transition matrix. Okay. So here I'm just since no one, I mean all of them have just leave this class. So here I'm just wrapping up my discussion today. If anything, anything you are not able to understand, you can put it in a discussion forum. We can discuss it over here, over there, or in the in the next class, you can come up with a confusion regarding the regarding this class. We also can discuss about this whole thing. I mean, whichever you find it efficient way to clear your doubts, we can clear all the doubts. So thank you everyone. See, meet you in the next class next week. Okay. Now I'm stop my recording. Thank you.